Okay, today is the last lecture. So sad, right? I made a few more small changes to the notes. But very minor. Because if I go through it again right now, as I teach, I will notice more. So update tonight, final. Today, if you go back and watch the Zoom, I noticed some very cool feature. Namely, that there will also be an audio transcript. That means that as I speak, right, the Zoom is automatically converting my voice into words. So even if you are deaf, right, you will be able to follow the lecture. Let's try out this feature. But I don't know whether it can transcribe math. Okay. Most likely cannot. Oh, I shouldn't talk so much. You should do this. So, hello. Hello. So you all know that the exam is in person, right? It's not going to be over Zoom or anything. It's going to be in person, I think 2 Fridays from now, something like that. I think it's E5 somewhere. Yeah, I prefer in-person exams. Everyone will do it in person except one person who will be over Zoom. Don't worry, it's not very difficult. But I think it's slightly more difficult than the previous year's ones. Every year it becomes more difficult. Every year become more creative. Can people in Zoom hear me? Yeah, okay, great. Thank you. So, yeah, so unfortunately, today is the last lecture. So we will conclude with estimation theory, and in particular, the conclusion of non-random parameter estimation. So last time we completed about Bayesian estimation, okay? So today we will talk about non-random parameter estimation, and in particular, we will look at the Cramer-Rao bound and the maximum likelihood estimator, okay? So what is the setting? It is really important for us to appreciate the setting and contrast it to the Bayesian setting where there is a prior on X. But here, there is no prior on X whatsoever. X is a deterministic parameter X. It is deterministic. It's like the mean of the Gaussian. And we would like to estimate the Gaussian, the mean of the Gaussian. Okay? So what do we have? Well, what we have is Y, which is generated from a certain distribution that is parameterized by X. So X is a parameter in this distribution. Okay? So what we would like to do is to design an estimator. An estimator is like a decoder. Oh, by the way, we start video so people can see me. So an estimator is nothing but a decoder. That means it looks at your Y and then it outputs a real number. Okay, so that is the meaning of an estimator here. Now the people here cannot see this, so let me readjust this a little. Okay, yeah, so that is an estimator. It's a function that brings us from the space of Y to the set of real numbers. We say that it is valid if it does not depend on what we are trying to find. So obviously, any meaningful estimator must be valid. Now, sometimes we are interested in bias estimators, but for the sake of stating the Cramer-Rao bound that we will state and prove later on, we will only talk about unbiased estimators. And unbiased estimators are those that upon taking expectation, which is written out explicitly here, we recover the true parameter for all X. Okay, so that's the meaning of unbiased estimator. Okay, so we'll be concerned with, in particular, admissible estimators, which are valid and unbiased estimators. Okay, now, among valid and unbiased estimators, as we have seen last time, the mean squared error is the bias squared plus the variance. That is the bias variance theorem. Okay, that we didn't prove, but you can look it up in any book. So the mean squared error is the sum of two things. But one of those things is already zero. The bias is zero because I enforce it. So we want to drive down the variance. We want the variance to be as small as possible. Okay, so we are seeking MVU estimators. In my notes, I call it MVU, minimum variance unbiased estimators. Okay, so those are estimators that have the minimum variance for all X. But these estimators do not necessarily exist, as we will show via one of the examples in the problem set, that you don't have to do it. Okay, so I will do it later on. It's very interesting. But if there exists, okay, and we will show that if there exists a minimum variance unbiased estimator, then it must be the maximum likelihood estimator. This is what we will show. It's only a one-line proof if everything is set up nicely. Now, regardless of whether there is a minimum variance unbiased estimator or not, any estimator has to satisfy the Cramer-Rao lower bound. And the Cramer-Rao lower bound is stated in terms of this information quantity, known as the Fisher information of the observation vector. Now, the observation vector can be a scalar. I just be more general. Okay, can be stated in terms of the Fisher information of the observation vector about the unknown parameter. So the Fisher information is about the random thing that you have. Okay, the Fisher information contained in the random observation that you have about the thing that you want to try to find. Okay, so this makes a lot of sense in Y about X. So it's defined as follows. And you may think that this is a little bit complicated, but it is not. Okay, so this is nothing but the expectation of some funny function of Y, like this. And a funny function of Y is the square of the derivative of the log of the probability distribution. And this guy inside here has a name. It is called the score. We'll define it properly later on. So the Fisher information is nothing but the square of the score function. Now, through two lines of algebra that we will do later on, we will show in this proposition that the Fisher information can be expressed in terms of the second derivative as well, the negative second derivative. And towards the end of the last lecture, I showed you that the Cramer-Rao lower bound is related to, the Cramer-Rao lower bound can be interpreted in an intuitive way in terms of the curvature of this log likelihood function. Okay, so we saw that the pickier the likelihood function, the bigger the curvature. Okay, go and watch the video. Bigger the curvature, and hence the smaller the lower bound. Because as we will show, as we will state Cramer-Rao lower bound later on, the variance is lower bounded by the reciprocal of the Fisher information. Okay, so let's restate that theorem. So we stated this theorem last time. We also drew a few pictures. If the family here, okay, satisfies the regularity condition, then the expected value of the derivative of the log of the density, there's a typo here. The more I look at this, the more there's a typo. So this should be uppercase. Equals to 0 for all x, okay? Then for any admissible estimator, and we know what's an estimator and we know what's an admissible estimator, then its variance evaluated at x, which is the variance of x at x hat y, is at least the reciprocal of the Fisher information. So I've already defined the Fisher information, so I don't have to write it down. Okay. So for any admissible estimator, we have this. So it means that the mean squared error, okay, if we constrain ourselves to unbiased estimators, must be at least this much. Then you may wonder, the good student among you may wonder, all right, is there an analog of the Cramer-Rao bound for biased estimators? Now, if there's a Cramer-Rao bound for unbiased estimators and it achieves a certain mean squared error, all right, because the mean squared error is bias squared plus variance, right? Then I'm sure you would know that people would have explored biased Cramer-Rao bound, all right? There's such a thing. If your estimator is so much biased, all right, it has a certain bias, then what is the best possible variance that you can get? So you can look up biased Cramer-Rao bound. Then you can also look up, another good student would say, all right, this is for non-random parameter estimation, right? How about if I know that there is some prior on the parameter x? Let's go back to the Bayesian case. Is there a Cramer-Rao bound for that? Yes, there is also these sort of things. So I have collaborators who spend their whole lives generalizing this Cramer-Rao bound. Okay, this is by the way called CRLB, Cramer-Rao lower bound. Okay, so there's a name for this theorem. It's discovered by Cramer and Rao, obviously, 1930s. Okay, and there are numerous generalizations of this. So last time I provided an intuition. I will not draw any more pictures now, but I will prove this. Okay, but before I prove this, are there any questions about how to interpret this result? Right. This is what we call in information theory a converse, an impossibility result. No matter how well you design your estimators, you will always have to suffer this loss. It is not a direct or achievability result. Any questions from the Zoom people? I think the proof is not very difficult, so we will do it. Who is this? Yen Fang Kang. Any questions? If not, let's dive into the proof. And it makes use of a certain lemma, which I will state. Okay, so before we prove it, let's state a lemma. Okay, so let Z and W be two arbitrary random variables. Okay, then we have the following. This lemma has a name, by the way. In case you want to Google it, this lemma has a name. It's called the Cauchy-Schwarz inequality for random variables. You know, there's a Cauchy-Schwarz inequality for vectors, so there must be a Cauchy-Schwarz inequality for anything. So let W and Z be two arbitrary random variables. Then say to make life simple, two arbitrary zero mean. Zero mean is not strictly necessary. You can adjust the means accordingly. Then we can consider their correlation. This is called a correlation. All right. But in the case of zero mean, this is called a covariance also. Then this guy here is controlled by square root expected value of z squared, expected value of w squared. Okay. So this is the Cauchy-Schwarz inequality. I won't prove it. The proof is from equation 71 to 73. Okay. We will accept this. So with the Cauchy-Schwarz inequality out of the way, we can prove our result. Okay, we can prove the Cramer-Rao bound. So recall that since our estimator x hat is unbiased, its bias is clearly equal to 0. Okay, its expectation of this is the error. Okay, which is equal to the expectation of x hat y minus x must be equal to 0. Okay, so the variance of E of y, by the way, whenever we write expectation and variance, it is with respect. We shouldn't put the little x here because we are averaging. Okay, so and B, note this and this are taken with respect to f of y parameterized by x. So it's taken with respect to the distribution that is parameterized by x. Okay, so that's what we mean by variance and expectation. So this is nothing but the second moment. Now, if your random variable has zero mean, then the variance is the second moment, right? So this is nothing but the lambda x hat of x. Okay, all this should be little x here, should be parameterized by little x, because we are taking expectation with respect to this guy here. Okay, so this is a method of setting things up. So in the middle of the proof, we should not define anything, but so it's very illegal, and you shouldn't write this in papers. But let's define something in the proof. Let's define the notion of score function. So we are going to define this score function h of y. It's just a function of y, which is given by the derivative of the log likelihood. Okay, so it's a derivative of the log likelihood. So it's a function of y, and it's also a function of x, but we will suppress the x for simplicity, just like we suppress the x in the expectations and variances throughout. So this is a score function, and you notice that, and I did this last time, if you differentiate the score function, h of y, then you are differentiating this guy here, right? If you differentiate, look at the score function, and what is the score function? Is the derivative of the log. So what we will have is we will put 1 over fy of y parameterized by x, and the derivative with respect to x of fy, y parameterized with respect to x. So this is the rule for differentiating log. Now, all this log is equal to log e, so that I don't have to carry around a lot of log things, okay? So usually when I do things, log is log 2. But here is log e. So this is a legitimate differentiation. Okay, so we notice the following also. What is the mean of h of y? Now, again, this is with respect to x, okay? What is the mean of this? So we did this last time already, okay? So expectation value of 1 over fy. Now I have to replace all these little y's with capital Y's, because these are random variables, okay? d by dx of fy, y parameterized by x. Okay, so this looks very ugly, but it's nothing but a function g of y. So we are basically taking expectation of a function of y. Okay, how do we do this? Well, we will just integrate over the distribution, which is this guy here, and exactly this thing here. Okay, so basically we have this. Okay, so this is the function of interest, and we are averaging over that particular distribution, fyy. Okay, and this integrated with respect to the whole domain y. Okay, I will not write down the domain. Okay, so now these things can cancel nicely, and so we are left with the integral of the derivative, right? We are left with the integral of the derivative, and what we have is that, okay, the regularity condition allows us to swap the integral and the derivative, okay, and we get the following. And last week, we already determined what this was because Priscilla answered this question. So this is differentiate 1, which is equal to 0. So again, not only do we have that the error has 0 mean, all right, but the score function also has 0 mean. So we have two conditions here, all right. So the error function has 0 mean, and the score function here also has 0 mean after a minimal amount of calculation. Now, if anything has 0 mean, then its variance must be equal to the second moment, right? Variance of h of y must be equal to the second moment of h of y. But what is this? This is nothing but the expectation of the square of the derivative of the log fy y parameterized by x quantity squared. And this, by definition, is the Fisher information in y about x. Agreed? This is just a definition. You can roll back this. Roll back the definition of Fisher information, one of the definitions here. Okay? So we set things up very nicely. Okay? Now we have got two random variables. We have two random variables. We have E of y and h of y, both 0 mean. Right? We have already proved this. They are 0 mean. Now we have two random variables. Just now I told you that we want to use the Cauchy-Schwarz inequality. So now is the time to use the Cauchy-Schwarz inequality. So what does the Cauchy-Schwarz inequality say? Well, it says that the expectation value of these two random variables, Ey, Hy, is controlled by the square root of the second moment of each one of these guys. H of y squared. Right? So we have this sort of simple relationship for the Cauchy-Schwarz inequality. Right? So the Cauchy-Schwarz inequality in the space of random variables says the following, because both of them have 0 mean. All right? So this Cauchy-Schwarz inequality can also be interpreted as the cosine of these two being less than 1. Cosine of the in a certain vector space, in a certain inner product space, actually, E of y, H of y, the cosine is less than 1. Okay, right. So we already have these guys here. Right. So this is less than 1. All right. So now we know that this is controlled by how much? The E of y is lambda x hat of x. Right. That is the variance of error. And this is the Fisher information, jy of x. So it remains to control the left-hand side. Right? It remains for us to control the left-hand side. Now, if the left-hand side is controlled to be 1, we are all set. And we are done. So now let's control the left-hand side. I'm doing this proof on the fly, so you're not really following this, but following my own train of thought. Okay, but everyone follows. These two random variables have 0 mean. We computed their means, and we also looked at their second moments, and they were respectively the variance as well as the Fisher information. Okay, so now it remains to control the left-hand side. So on the left-hand side, we have E of y and H of y. Okay, that's the covariance, okay, if you wish. So that is x hat of y minus x, that's the error. And you have d by dx of, oh my gosh, this is missing, right? No, it's not missing. D by dx of log of f of y, yx, okay, and we don't have enough space. So we move it down here, okay. Now this is not quite correct here, so let us do this properly. This is an expectation, right? So what is meant by expectation? You need to take average over this guy here, and you have d by dx, that's the log of y, yx dy. Okay, so where do all this come from? The expectation results in this guy here. Next thing here is the ey, basically this error is this guy here, that's the error. And lastly, we have the score function is this score function here. So you can see all the elements here properly, right? Cool. The averaging, the error, the score function. Okay, so now this guy here can be differentiated. It is going to be 1 divided by fy yx of derivative with respect to fy yx as usual. And beautifully, this cancels this, right? And so what we are left with is the integral over the error of the derivative of fy y parameterized by x dx. Okay, right. Okay, so let us split this guy here to d by dx integral of x hat y f of y yx dy. Okay, so where does this come from? Well, this comes from taking this part and this part, merging them together. Okay, this comes here. Okay, and I'm going to run out of color soon. So the next part here is minus, all right, x integral d by dx of fy y parameterized by x dx. Okay. Thank you very much. All this should be dy. Thank you very much. Okay. So what do we get here? Here's where we make use of unbiasedness, right? So what is the meaning of this guy here? This is nothing but the expectation value of x hat of y, which is equal to x due to unbiasedness. Unbiased. How to spell unbiasedness? Unbiasedness. Okay, so that's unbiasedness. This equal to x. Secondly, people in the audience should know that I can swap these two things, and I'm going to swap them now. D by dx of the integral. If you allow me to swap them in one line, then this is equal to, this integral is equal to 1, and the derivative of 1 is equal to 0. So 0 times x is still 0. So the second term is equal to 0. And now your d by dx of x, what did you get? On the left-hand side, on the left term here, this is 1 minus 0 is equal to 1. Okay, so this calculation is marginally involved. So let me go through this one more time. I think these calculations above are not so involved, considering the second moment. But this correlation is a little bit involved. So let's go through it one more time. And hopefully I don't write dx ever again. So this expectation, you are taking average with respect to this distribution. Okay, this error is here. The h of y is a score function, which is here. The score function can be differentiated to be 1 over the density and the derivative of the density. That's how we differentiate log. What rule is this called? Chain rule, I think. Chain rule. Now, this very nicely cancels this. And so we are left with the bias term as well as the derivative of the density term. Now, because integration is linear, okay, this is not so trivial fact, but integration is linear, right? So we can take this and marry them together, okay? And we can take this and marry them together, but the x is outside, so it can go outside the integral. And then the derivative is here. But everyone in the audience knows that because of the regularity assumption we made, we can swap the derivative and the integral. And the integral of the density is 1. And so the derivative of 1 is 0. The second term vanishes. The first term, however, is marginally involved. But you would notice, and the perspicacious student in you would notice that this is the expectation of the estimator. And this is nothing but equal to x. And here is where we make use of unbiasedness. Unbiasedness. Actually, we did make use of unbiasedness up there also to declare that the error has 0 mean. Okay? But this is making use of unbiasedness in a very serious way here. Right? Very serious way. So the d by dx of x yields 1 below 1 minus 0, 1. So to conclude, we have that this is equal to 1. Okay? And so we have this inequality, beautiful inequality here, that this is equal to, this is less than equal to this, but the left-hand side is equal to 1. Right? And so by simple rearrangement, the variance of any estimator, which is equal to lambda x hat of x, this is just some strange notation, is greater than 1 over the Fisher information. And this completes the proof. Okay? So this is a matter of the application of the Cauchy-Schwarz inequality. Right? This is the proof of the Cramer-Rao bound for unbiased estimators. You can be very creative, right? You can write numerous papers on this. Unfortunately, a lot of people have already written papers on this. Right? So if I have a little bit of bias, what is the best variance? Right?
So how to prove that this is a tight bound?
How to prove that this is a tight bound? Through some examples. We can construct some examples to meet the Cramer-Rao bound.
The
Equation can be equal. The next example shows. Okay, it's very easy. But sometimes it is not tight. Okay. Sometimes there's no. Sometimes okay. If the Cramer-Rao bound is tight, then the estimator that achieves the Cramer-Rao bound is the ML estimator, maximum likelihood estimator, as we will prove later on. Okay, but the Cramer-Rao bound need not be tight. Okay, and so the ML estimator may not be tight. It may not be tight in the sense of achieving this with equality as well. Okay. So I mentioned last time that we need the regularity condition, and so there are some examples here to show that the regularity condition is needed. Okay, so I will not belabor the point, and I will go to some simple example. Okay, but before that, I want to ask whether you have any questions concerning the proof of the Cramer-Rao bound. I probably won't ask you to prove the Cramer-Rao bound in the exam, because it's out there. So there's no point of you proving it, but you need to know how to use it. But this proof is simple enough for you to appreciate it. Right? Simple enough. Any questions about the proof? We have lots of time. Today I won't.
The regularity condition is just saying that you solve the integral and the derivative.
Yeah, that's right. That's right. Yeah.
Because from the lecture, it sounded like you started with expectation of hy equals 0.
Yes, yes.
And then you work downwards.
Yes, yes. I mean, whenever we use the fact that you can do this, right? Whenever you use, okay, originally this was derivative inside, and then we swap this. But really what we have done, right, is we have made use of the regularity condition. Because if I didn't do this derivative here and I worked with this part here, can you see this part here and I integrate this? This is nothing but sorry, I am circling the wrong thing. Here, if I look at this and I integrate this, what I'm doing is I'm invoking the regularity condition is equal, regularity condition, expectation of this score is equal to 0. Okay. Yeah. So, I mean, we can state the regularity condition in terms of exchanging these two operators.
Yes, because I'm not sure whether it will be true that given the regularity condition is true,
Yeah.
you're allowed to swap the operators. You get me?
Yeah. Actually, we should. I don't know why I stated it this way, but expectation value of a score is equal to 0. And whether it is the same as we can swap these two. I suspect it is equivalent. Yeah, but I will not do it here. Maybe I'll do it offline. But I suspect that the fact that the score has 0 mean implies this is equal to 0. Okay, because we can work backwards, we can work with this guy here. We can work back. The way I've done it is a bit different because I differentiated this before swapping this. So I'm making use of some other regularity condition. That is not very kosher, I know. Yeah. So I noticed that there's some slight subtlety here, but we don't really have to worry too much about it. Okay. So rather, I would like to go to an example in order to show this student here that this bound can be tight. Okay. So y is equal to x plus w. This is the simplest possible thing to think of. And w is Gaussian noise with certain variance. Okay. So we're going to figure out the Cramer-Rao bound. Okay. So log of fy, y parameterized by x. So that is basically we have f of, did a student come in? I thought I saw something. No, okay, good. So now we have yx, so this is equal to 1 over square root 2 pi sigma squared e to the minus y minus x quantity squared over 2 sigma squared. That's the Gaussian. So if we take the logarithm, we get minus y minus x squared over 2 sigma squared plus some constant that doesn't really worry us because we are going to differentiate this anyway. Okay, so now we are going to differentiate this with respect to x. So the constant comes from the pre-constant term here that I don't want to write down. Okay, so oh my gosh, some typos here also. This is equal to 1 over sigma squared, okay, x minus y. All right. So this is nothing but differentiating this with respect to x. Okay, so let's see. Yeah, this is the right direction. I'm always concerned whether there's a minus here, but this is the right direction because I expanded this in my head to differentiate. Okay, so now this is nothing but 1 over sigma squared of x minus y is minus w, so we put a w here. Okay, so hence the Fisher information is given by 1 over sigma 4. So we need to, okay, let me write down the definition one more time. This is nothing but the expectation value of the square of the score. This is above is the score. So that's how we evaluate the Cramer-Rao bound. Huh? So slowly do this. Later I'll show you some other examples. Okay. So now we have to square. We have to square this guy here that we have found. Okay. So you will have to take power 4 of the sigma, and you will have to take the square of w. All right. So what's the square of w? W is 0 mean, right? So that's the variance. So this is just 1 over sigma squared. Right? Because the w is this is variance of w, and the variance of w is sigma squared. So the sigma squared and sigma squared cancel. So you are left with 1 over sigma squared. Okay, so what do we have? All right. What do we have? So the CRLB states that any estimator x hat mapping from R to R, because Y lives in R, okay? Any estimator must satisfy, in fact, that its variance evaluated at X must be bigger than 1 over JY, 1 over the Fisher information, which is sigma squared. So that is how we evaluate the Cramer-Rao bound. Okay, so is this calculation clear? Before I go into what I want to talk about next. Is this calculation clear? Any questions on calculation? Yes.
Sorry, I think there's a small error, like 1 over sigma squared W, that should be minus sine. Doesn't really make much of a difference. Because y is x plus w. So.
No, correct. X minus y is what? X minus y is minus w, minus becomes plus. You think about it. I think I'm right. If I'm wrong, I will say I'm wrong.
No, y equals x plus w, right?
Y equals x plus w, so x minus y.
Minus w.
X minus y is minus w, then the minus and the minus, this minus and this minus marry each other to give you nothing, right?
But then if you use the second form of the Fisher information, it takes the second derivative.
Okay. Okay, let's see whether we can show that the second derivative form is also the same Fisher information. Okay. Okay, so the first derivative is this one. Okay, so we're going to cut it here so that we don't cheat and I don't pull a minus sign out of the hat in any case. Okay, so okay, I want to say a few more words about an estimator that achieves the Cramer-Rao bound, but just to satisfy what's your name, Jing Yang's curiosity, let us differentiate this one more time. Okay, let's see whether I can differentiate this one more time. D by dx squared of logarithm of fy, y parameterized by x is equal to minus 1 over sigma squared. Okay, so we keep all the minus around properly. All right, so now what's the Fisher information in the second form? We need to stick in a minus into expectation of the second derivative of logarithm of fy, capital Y x. All right, So now we get 1 over sigma squared. Cool, right? No minus sign missing, right? Even though I'm doing this in public, right? So, so the two calculations dovetail, all right? And so the Cramer-Rao lower bound is as follows above, okay? The Cramer-Rao lower bound is as follows. So now, remember what is the story? The story is y equals to x plus w. W is zero mean, okay? So now you observe, or we observe y. And we want to guess x. So what estimator should we choose? So we are mapping y to guess of x. So W is zero mean. Priscilla, what estimator should we choose? How should I design x hat y? In a logical way. Equals to y, all right? So equals to y. All right, cool. Now, this is our estimator. Is it zero mean? Okay. Now let's evaluate its, so not zero mean. Is it unbiased? So that is equal to expected value of y, right? What is the expected value of y? Is exactly x. Hence unbiased. Okay, so this estimator that Priscilla gave us is unbiased. So we can see whether it attains the Cramer-Rao bound or not. Okay, so we can compute its variance of x hat of y. So that is variance of y. That is variance of x plus w. Is y is x plus w, right? Okay, the variance of x plus w is the same as variance of w. And it's the second moment of w, which is sigma squared. Okay, so what does it mean? In this favorable case, the Cramer-Rao bound is attained with equality. In fact, this estimator, this estimator here is known as the maximum likelihood estimator that we will discuss shortly. The Cramer-Rao bound is attained with equality, and hence our estimator is efficient. When an estimator meets the Cramer-Rao bound with equality, we say that the estimator is efficient. All right, we should properly define this in a definition environment first. So you see, we have made an example and we have computed the Fisher information and we have suggested an estimator for which the Cramer-Rao bound is met with equality. All right, so no other estimator can do better than this variance here, sigma squared. Okay, this is a favorable example. There are many examples that are not favorable, very ugly. However, all right, in real life, when we actually do research, we don't see a one-shot thing like that. We don't see a y and then we guess x. Usually we see many copies. Asymptotics, we like to do analysis. That means a lot of things happening and we convert something, right? So when we have a lot of things and we do maximum likelihood, even if the maximum likelihood estimator is not efficient in this sense, right? If some regularity condition holds, the maximum likelihood estimator can be shown to be asymptotically efficient. That means it's, as n tends to infinity, we get closer and closer to the Cramer-Rao bound. All right, so that is something for a statistics class. Anyway, so do people understand the calculation in this example fully? I let you stare at it. Stare at the handwriting. People in the Zoom, any questions? I know some people here like to ask me questions. Xing Jian, you like to ask me questions? You any questions here? Can you follow all the calculations here? No, no response. Never mind. We will, let me see, 39. All right, so before I go to maximum likelihood estimation, right? So I owe you the proof of this this condition here that the Cramer-Rao, the Fisher information can take on two things at the same time. Proposition, all right? So the proposition states that we have these two forms of the Fisher information. Okay, so this is a matter of differentiating things carefully, but I think it's worthwhile doing it because it teaches you how to differentiate things properly. Okay, the proposition is that this is equal, the Fisher information is equal to this square of the first derivative of the score function but it's also equal to the negative second derivative of the log likelihood. Okay, so proof. All right, so this is not very difficult. So first observe that the integral of any density is equal to 1. I will not put in the limits, okay? So differentiating this with respect to x, what do we get? All right, so assume as usual that we can swap, all right? Assume that we can swap, then what we get is the following. Okay, we differentiate this with respect to x, so we have, I'm sorry, d by dx of dy equals to 0, but the derivative of the score is equal, the derivative of the density is equal to fy, y parameterized by x, the derivative of the log of fy, y parameterized by x dy. Okay, this requires a moment of thought. Okay, so this guy here is a consequence, and I should be consistent. This is the partial, if I wish. Okay, so this guy here is the same as this guy, because if you do this in your head, right, you will put the log, you put the density below, and you have cancellation, and you will differentiate the density. We've already done this several times, so I will not belabor the point. Okay, so now looking at equation star, differentiating star one more time. Okay, then we will have the following. Okay, we will have fy, y parameterized by x. We use the, what is this called? The multiplication rule, product rule. Okay, so we have, you can differentiate, double differentiate with respect to the logarithm of the likelihood. Okay, plus now you fix this logarithm of this, and you differentiate that, right? Differentiate that fy, yx. Okay, and I'm running out of space, dy equals to 0. So now you will see that this is equal to this left-hand side is equal to the expectation of the second derivative of fy, y parameterized by x. So this is a consequence of noticing that this is the expectation of the derivative of the second derivative of log. Okay, so now what we are going to do, this is not quite it yet, not quite finished yet. So this part here, right, is equal to one more copy of this, right? This part here is fy, y parameterized by x of logarithm of fy, y parameterized by x. So now, at this point in time, what you do is you marry this guy here with this guy here, and so you get a square. And outside here, this guy here is an expectation. So what you have is plus expectation of the square of the score function, and this should be uppercase, equals to 0. And so if two things are equal to 0, one thing is a negative of the other. And so this, we first define this as the Fisher information. And so the Fisher information is equal to the negative of this guy. So this completes the proof. So this is a matter of what I like to call, and what some students like to make fun of me of, as bookkeeping. This is bookkeeping, right? Bookkeeping means you be very careful. Now, I tend to make a lot of mistakes when I'm doing this in public, but if I didn't make mistakes, that means it's probably okay, right? I just basically did bookkeeping here. So you see, now we have two different representations of this Fisher information. And what we have done now, this comes from the square here, okay? What we have done is we have two representations. Often in practice, it is easier to use this representation because we just have to differentiate twice, as we will see later on. Differentiate twice is easier than squaring something and taking expectation. Okay? Now, any questions about this calculation? By the way, I forgot to say something. Just now I stated the Cauchy-Schwarz inequality, right? Later I'll talk about it again. Right? I just think that you have Cauchy-Schwarz inequality. When do you get equality? You get equality when one random variable is a scalar multiple of the other. And this is kind of important later. Any questions about this example? No? Okay. So we will now proceed to maximum likelihood estimation. Okay. And we'll see using a one-line proof that maximum likelihood estimation, maximum likelihood estimates are if there is an efficient estimator, it must be the maximum likelihood estimator. So maximum likelihood estimation is the first thing that you would think of when you want to do estimation of non-random parameters. This is the algorithm that you will use. Maximum likelihood estimation. Definition. Okay. D. By the way, I wrote D in my notes right here. But some people might find it objectionable to use D here, especially proper mathematicians. Because there could be many, right? But never mind, let's just be very loose. I don't want to be racist. But there could be many, right? Because your density could be flat. Okay? So whenever you write something, especially write a book or write a paper, we have to be careful, but this is not quite acceptable. Okay, X hat, MLY. The MLE, okay, is defined as, so the MLE is a certain estimate given the observation vector Y. Oh, by the way, just now the proof for the Cramer-Rao bound I did only for scalar observations. So when you have a vector Y, right? Then what do you have? You have what is called the FIM, Fisher Information Matrix. And the Cramer-Rao bound is in terms not of this ordering of variance greater than something, but it's about the covariance of a certain estimator is greater than the inverse of the Fisher information, but the greater than is in terms of the positive semi-definite order. So you know what's a positive semi-definite matrix? Okay, all the eigenvalues are bigger than 0. So that's a generalization of the Fisher information and the Cramer-Rao bound to the vector case. Okay, so we need to talk about Fisher information matrices and PSD-ness. Okay, but never mind. We are only talking about scalars, right? But here we're talking about vectors. We're toggling. The MLE, maximum likelihood estimate, is defined as the estimate that maximizes the likelihood. So this is a very nice definition. Argmax over X of this guy here. So this F is called the likelihood function. So how likely are you to see Y when the ground truth parameter is X? So we are basically just argmax this. Okay, so that's the maximum likelihood estimators. So definition, an unbiased estimator. Okay, it must be admissible also. An unbiased and everything is valid. Okay, I'm not going to say valid. An unbiased estimator is efficient if it satisfies the Cramer-Rao lower bound with equality. So this is a super favorable scenario, very beautiful scenario that, you know, we have efficient estimator. All right, sometimes we do, many times we don't. All right, so sometimes we do, as we will see in a couple of examples, but many times we don't as well. All right, so what is the subsequent objective? What do we want to do now? Okay, what I've introduced here is the maximum likelihood estimator that you can compute through some calculus, as we will do very soon. But we want to show that if there exists an efficient estimator, then it must be the maximum likelihood estimator. Okay. Now all our densities are differentiable. Okay, from now on. Okay. Right. So our objective is to show that if an efficient estimator exists, it must be the MLE. Okay, this is do you find that this is a interesting result? I find that this is very intriguing, even though it can be only proved in a few lines. Okay, so this is the objective, right? How to achieve this objective? Look at what is meant by efficient. That means we meet the Cramer-Rao bound with equality. Now, when we consider the Cauchy-Schwarz inequality. That was what resulted in the inequality in the Cramer-Rao bound. That was where we got an inequality. So that was the Cramer-Rao bound, right? This is the Cramer-Rao bound. So when does the Cramer-Rao bound satisfy with equality? Consider the Cramer-Rao inequality. It is an equality if and only if Z is equal to CW for some constant C. Okay, so I mean, this Cramer-Rao bound, right, is basically talking about the cosine between two vectors. Cosine cannot be more than 1, right? So when is the correlation between two vectors maximum? It is when they are collinear, right? So this means you can think of random variables as vectors also, and they are in some inner product space. So here, I mean, it is easy to check this statement. I'm not going to prove this statement. Okay, it is an equality if and only if the two random variables are scalar multiples of each other. Just you mean the whole thing 0? What if C is 0? C is 0 is okay, right? This is equality. Because if C is 0, Z is almost surely 0. Then the left hand side is 0, the right hand side is 0. Right? We allow C in R. All right. Okay, it's an equality if and only if this is true. But so when we prove the Cramer-Rao bound, we were looking at the correlation. Recall, we were looking at the correlation between this guy and that guy. And we were relating it to this guy, the second moment, and that guy, the second moment of that guy, the score. Right? We were looking at this. So in order to enforce equality here, equality in the Cramer-Rao bound holds. If and only if there exists some constant k of x. Now this constant, right? Note that when we did this, all these are dependent on x. I already said, okay, that all the expectations here are dependent on x. Everything here is dependent on x. So now this constant also depends on, it's not quite a constant, it's constant with respect to y, but not with respect to x. That we have Ey equals to kx hy for all y. That is a condition for the Cramer-Rao bound to hold with equality. That is this random variable Ey, you can put uppercase y on it, right, is equal to the score function up to a constant. Then the Cramer-Rao bound that we applied here would be an equality. Correct? Definitely right. Because I said that Cauchy-Schwarz inequality if and only if this is true. Okay, so what does this mean? All right. Thus, efficient estimators would have this property. And now we can unravel this because the left-hand side is equal to the difference between our estimate and x. That's the Ey. And k of x, let's keep it there. The score function is given by the derivative with respect to the log density. Okay, so this can be rewritten somewhat, is equal to this plus this. Right? So what property do we need? Okay, so if an efficient estimator exists, it must take on this form. But look at the right-hand side. We need the right-hand side, okay, to be independent of x. for it to be valid. Right? Now, the way that the right-hand side is written, seems like there's a lot of stuff that is dependent on x. Right? But remember that we want our estimators to be valid. So, not only do we enforce equality in the Cramer-Rao bound by enforcing the error and the score to be linearly related, but we also have to ensure that what results on the right-hand side here does not depend on x. Okay? So, let us compute, let us see whether this thing can depend on x or not in a later calculation.
Okay.
But, oh, someone is talking. Someone is not muted here. Sorry, sorry. Oh, Mohammed is not muted. Let me mute him. How do I do this? Okay, now he's muted. Good. Right. So, I thought someone was asking me a question. So, now let's compute the second moment. All right. So, this is equal to EY. All right. One more copy of EY, which is K of X, H of Y. Right. Now, the K of X has got nothing to do with this. Has got nothing to do with the y, so we can bring it outside, h of y. Okay, so this is nothing but this part here we have already ascertained is equal to 1. So k of x is equal to this guy here on the left hand side, but this guy here is the error, the variance of the error. And if this is equal to, and if the Cramer-Rao bound holds with equality, this is equal to the inverse of the fixture information. Okay, I think I went a little bit fast here, but here's the second moment of the error. Okay, I want to figure out what is this k. All right, this k seems to be something magical. So let's use some equalities to figure out what is this k. So let's look at the second moment. Let's keep one copy of the e. And let's put E, the remaining copy, to be this inside here. Okay? So this has got nothing to do with the expectation over y, so it can come out. But in our calculation just now in the Cramer-Rao bound, this part is equal to 1. Okay? This part was equal to 1 by using some regularity conditions. So kx is this entire expression. But if the Cramer-Rao bound holds with equality, this holds with equality as well. Because the variance must be exactly equal to the reciprocal of the Fisher information. And hence this guy here, all right, this guy here cannot be arbitrary. The kx cannot be arbitrary. It must be the reciprocal of the Fisher information through this calculation. So if an efficient estimator exists, the right-hand side must be independent of x. Okay? The right-hand side must be independent of x for an efficient estimator to exist. Sometimes it is independent of x, sometimes it is not. But the way we have written this in this way, okay, suggests something. Okay, an efficient estimator takes this form. And we can verify something. It is automatically unbiased. Okay, how do we check this? We can just take the expectation of this. Okay, so we can take the expectation of x plus 1 over jy of x, and this is the score. Okay, so this entire thing here, this derivative here is the score, h of y. This part here. So now x is a constant, it can be brought outside. This is also a constant, right? So this is also a constant, and this is the expectation of the score. But the expectation of the score by regularity is equal to 0, so we get that. So if any efficient estimator takes this form, it must be automatically unbiased. But what makes an efficient estimator efficient is that the right-hand side here must be independent of x. Okay, must be independent of x. Okay, So how is an efficient estimator related to maximum likelihood estimator? I made this observation. Our objective is not achieved yet, okay? What we want to show is that if an efficient estimator exists, it must be the MLE. And we have the form of an efficient estimator. We check that this efficient estimator is indeed unbiased. That's a good start. But if it exists, we want to show that it is the MLE. Okay, so theorem. Okay, by the way, before I state the theorem, is there any question on the calculation here? Any question on this calculation? I think it may be a bit involved, but it is what it is here. Right? Very clean, right? Very neat. So the point is that we try to look for a condition of equality in the Cauchy-Schwarz inequality. All right, and that's what we obtain. EY equals to K of X, HY. And then we recall the definition of H is basically the score function. And then the error is basically the difference of these two guys. But this K cannot be arbitrary. And we will show that it is equal to the reciprocal of the Fisher information matrix. So how to show this is just a train of equalities here. Okay. So what we have is that any efficient estimator must take the form in the box. Okay. And it must take the form on the form on the right-hand side. And if the right-hand side is independent of X, automatically we have efficient estimator. We have the estimator is efficient. Okay. But the next thing we want to show is the following. When an efficient estimator exists, it is the MLE. Okay. i.e. X efficient dot equals to XML dot. Okay, so maximum likelihood estimators have a very special place in our hearts because they are the only candidates to be efficient. No other candidate. Okay. So proof. So any efficient estimator can be written in the form X plus reciprocal of the Fisher information of the derivative of log Fy Yx. Okay. So now, since the right-hand side, since we are in the business of efficient estimators, since the estimator X is efficient, which is very funny, the right-hand side does not depend on X. Right, the right-hand side does not depend on X. So let's substitute a convenient substitute. X equals to XML. It will not change the left-hand side because the right-hand side is independent of X. Okay? The right-hand side, we can substitute anything inside. All right? So what happens here is that let's look at this guy here. Derivative of X log of Fy, Y parameterized by X, evaluated at X equals to X hat ML, Y. Okay? So what are we trying to say here? All right. The right-hand side does not depend on X. So we are free to plug in any values of X. And in particular, let us plug in the value of X that is the maximum likelihood estimator. All right. So this guy here automatically becomes the maximum likelihood estimator. Okay. What does this guy, this very heavy stuff become? All this stuff. What does it become? All right. So let's look at this. This derivative is a function of the thing, right? Of the variable you differentiated against. So let X be equal to XML. Okay. Now, let's recall that XML hat is equal to the argmax over X of the F of Y parameterized by X. That's the meaning of maximum likelihood estimator. But equivalently, as you know, I prefer to stick a log inside because most densities are exponential family. So we stick a log, makes life easier for us. All right. And I said that everything here is differentiable. So the point here is that d by dx. So how are we going to evaluate the maximum likelihood estimator? we are going to differentiate this log thing here and set it to be equal to 0. So the xmly is such that when you take the derivative with respect to this log here, it is equal to 0 by stationarity. So this guy here is exactly equal to 0. And what do we get? That this guy goes away. And so we are recovering that this entire thing, let's undo this a bit. This entire part goes away by the stationarity of the maximum likelihood estimator. The maximum likelihood estimator is a stationary point. All right. And this recovers XML hat y. And we are done. So I told you, if you know what you're doing, it's a one-line proof. Okay. One more time. What is the statement? The statement is that if an efficient estimator exists, it must be the maximum likelihood estimator. Why? Because all efficient estimators look like that. All efficient estimators must look like that. And the right-hand side must be independent of x. Independent means does not depend on x. Not independent in the sense of random variables. Okay, so since it is independent of x, we are free to substitute anything we want. So let's substitute x equal to x hat ml. So this guy here, x. Okay, those people in Zoom cannot see like that. So this guy here is XML. So this guy here better have be 0. But indeed it is 0 because XML is defined like this. Okay, with the log it's more convenient. Okay, so everything is differentiable. We can differentiate this and set it to 0. And by the stationarity of XML, when you evaluate this guy at XML, this will be equal to 0. And hence this thing is true. Okay, and hence this goes to 0 as desired. Okay, pretty nice, right? And this theory is beautiful. All right, this theory is really beautiful. Okay. Okay, so just a small little remark. We have already proved this. Okay.
Prof, could you just explain again why the right-hand side is independent of that?
Because any efficient estimator must be valid. Valid means the estimator cannot depend on the unknown parameter. The way we have written this, which comes from here, you see the right-hand side here has a lot of things to do with x. But these x's must somehow cancel nicely in order for an estimator to be valid. Efficient estimators are those that meet the Cramer-Rao bound. Those estimators that are involved in the Cramer-Rao bound are admissible. Admissible means what? Unbiased and valid. So efficient must mean valid. Understand? Okay.
Is there any way to know when the efficient estimator exists?
Well, it's not too difficult. You can simply calculate the right-hand side here and see if it depends on x. Okay. We will see some instances later on in which an efficient estimators do not exist because the right-hand side here depends on x. Okay. Actually, it's not so easy to tell sometimes, but if it is easy to tell, it is easy because this is easy to calculate. If this is easy to calculate, it's easy to check. Does that answer your question? Okay, if this is easy to calculate, then it's easy to tell if an efficient estimator exists. But if it's not so easy to calculate, then it's not so easy to tell whether an efficient estimator exists. Right? And this is the answer. Actually, my answer makes sense. Right?
So that provides us with a way to check.
Yes, yes. It provides us with a recipe to check. Whether or not this recipe can be executed is another issue. Because sometimes you may find it difficult to compute the Fisher information matrix below. The Fisher information thing below. Okay, it's not matrix in this sense. Yeah, in the vector case, you need to do matrix. Okay. So it should be stressed, as I mentioned here, that the MLE, maximum likelihood estimator, need not be efficient. Okay, because it need not even be unbiased, as some example will show. So let's do this favorable example. I'm only going to do example 6. The Poisson example you do by yourself. Okay, so example 6 is this. We are very familiar with the exponential distribution. Okay, so this is parameterized in a rather strange way. Okay, so in this case here, the mean of y is equal to x, and all x is greater than 0. So when we talk about Poisson, right, we usually write like this, right? When we talk about Poisson, but here the variable is y, and the parameter is x. Okay, and the mean of this guy here, the mean, say if the inter-arrival time x is distributed like this, then the mean of x, I think you recall, is 1 over lambda. But so here I'm parameterizing like 1 over x, and for a good reason, because later we'll parameterize it differently. Okay, so suppose we observe one sample. Observe y. What do we guess about x? Okay, so let's compute the MLE. Okay, so now the log density is should be very nice. It is given by minus log x. All the logs are natural log minus y over x. Right, that's the log density. So now we can differentiate the log density to get the score. So assuming my differentiation is professional, we get this, and we get that xml, which is a function of y, is equal to y. Correct or not? Cancel. I think it's correct. 1 over x is equal to y over x squared. We cancel this. Yeah, x is equal to y. Okay. Right. So that's the my maximum value estimator. Okay, of x. Cool, right? So what is the lambda, the variance of my estimator? So that is variance of my xmly. Now I have to put in capital Y, right? That is nothing but variance of y. But you know that, hopefully by now you know that you're familiar with this distribution, and the variance is nothing but x squared. Now in Poisson processes, right, we recall that we actually write this sort of thing: f of x is equal to lambda e to the minus lambda x, indicator x bigger than 0. The expectation value of x is 1 over lambda, and the variance of x is equal to 1 over lambda squared, I believe. Okay, so here we have x squared. Okay, so now let's compute the Fisher information. So that is nothing but the expectation of this guy here. Log of fy, y parameterized by x, we take the quantity squared. Okay, this is very painful because actually we should differentiate one more time. Okay, but we can square y minus x over y minus x squared over x4. Okay, after we do some careful bookkeeping. So we are basically squaring this guy here. So we have y minus x, y minus x all squared over x4. All right, because this guy, sorry, now I'm doing algebra. I shouldn't be doing algebra. This is y minus x over x squared. Correct? Yeah. Okay. So we square that red thing. Okay. Okay. So we have a 1 over x4, and the top is variance of y. Right? Because the mean of y is x. So you take the expectation of this guy here, that's nothing but the variance of y. So you have to be pretty fast. All right. So variance of y we've already ascertained is x squared. So this becomes 1 over x squared. There's some cancellation. Right. So we have that lambda ml of x is equal to, this is very messy. We have lambda ml of x is equal to what? Is exactly equal to the inverse of the Fisher information. Okay, and this implies that for this favorable scenario, the Cramer-Rao lower bound is tight again. Okay, so this is some calculation. So here I then take second derivative. I just take the first derivative and square it, and I observe what is my Fisher information, And I noticed that the variance here is related to the inverse of the Fisher information. And so the Cramer-Rao bound is tight. Any questions on this calculation? Any questions from the people in Zoom on this calculation? Can see here. All this is typed out. How to equation 96? My God, how to equation 96? Zheng Tian. Equation 96, is it this one here? The X efficient XML. Is it this one? I cannot see also.
I think the maximum likelihood estimator equal to 1.
No, there are different versions of what my notes. So I don't know. What do you think is the equation 96?
XML equals to 1. The maximum likelihood estimator is 1. Yeah, you can pull up. Okay.
Yeah. Oh, it's because the derivative of the log is evaluated at XML. Okay, so remark. Okay, thank you for the question. So this is to answer Zheng Tian. I don't know whether it's equation 96. Is it the example or is it the thing before the example? Jin Yan.
Wait. It's the one where you showed that the derivative of the log fy is 0.
Okay, because equation 96 is because XML y is argmax of log fy y parameterized by x over x. So this is your curve of log fy y parameterized by x as a function of x, and this is the maximum point. Okay, at the maximum point here, the slope, the derivative, okay, so here is x mly. At the top there, this is the curve. At the maximum point there, what is happening is that the slope evaluated at x equals to x mly must be equal to 0, because what's happening here is that we have a stationary point. This is flat here. That's the meaning of derivative. Zheng Tian, understand? Oh, okay, good. Yeah. Okay. So you can read example 7 on your own on Poisson. Okay, it's a matter of calculus. Let us do something more exciting. Okay, let us revisit this Poisson example. No, this is not Poisson. This is exponential. Let's put it here. Let's look at this example with Vincent. And we have more friends joining us too. Just now I saw one person joining. Okay, so let's look at this example with Vincent. And now let us reparameterize things like the following. Oh, so now we are reparameterizing the distribution so that it looks like this. Okay, so the expectation of y is equal to how much? 1 over x. Like the x is the lambda. Okay, for our inter-arrival times, the x is like the lambda. Okay, so in this framework now, is the maximum likelihood estimator efficient? That's the question. Okay, exam question. Is the MLE efficient? Just now the MLE was efficient. In the next 5 minutes or less, we'll prove that the answer is no. And we don't even have to go through this Cramer-Rao bound business. Okay, so now let us compute the MLE. Okay, so let's take log first. So that is log x minus xy. Everything is base e, right? Now we take the derivative of the log likelihood. Okay, how to differentiate log? We will have 1 over x minus y set to be equal to 0. So XML hat Y is equal to 1 over Y. Right? Everyone follow my algebra? This is not typed out, so you can just look and I will upload this, of course. So this is my maximum likelihood estimator. I want to ask the question, is it efficient? Then there are several things you can do if you want to answer this question. The average student would go and continue and compute the Cramer-Rao like this. The average student. The good student will stand hard at this and first compute the bias. X hat ML Y equals to expectation value of 1 over Y. Okay. So Y is distributed. So what do we hope for if it's unbiased? Okay, is it unbiased? If it is unbiased, this one should be equal to X. Right? If unbiased. If. Oh, okay. If unbiased, this should be true. Okay, so now let's compute this guy here. This guy here is nothing but this guy here. How to compute this? Now, if the reciprocal and the expectation commute, which it doesn't. So we put question mark here. Say it commutes. Then, yes, very good. Then you will have expectation value of Y is 1 over X, so you get. If this commutes, if you can interchange reciprocal and expectation, but it doesn't. This doesn't hold, and there's a strict inequality here. It goes one way by Jensen's inequality. 1 over X is convex. So this goes in one direction, and we have to think a little bit which direction it goes in. It's not difficult to figure out because 1 over X is convex, but this is not equal. And so we don't even have to talk about Cramer-Rao bound. We don't even have to talk about the calculating the Fisher information because it is not unbiased. Okay, so for the exponential distribution, it is important to, if you want to do maximum likelihood estimation, it's important to parameterize it in this other way. Okay, if you parameterize it in this way, then the MLE exists clearly, but it is not efficient because it is not unbiased. Okay, so now any more questions? Nope. Here, any more questions from the audience here? We take a 15-minute break. If not, then I will do a couple of questions from the homework. Couple, maybe 3, depends on what you want. But I want to do one question in particular. Okay. I want to do the first one and the very strange one on W1, W2. Question 4. And let's see whether you have enough time to do more. Okay, so we take a 15-minute break. We come back at 38. Okay, 7:38. And people here should ask me to. Okay, I want to spend a few moments just doing some problems. You have already got all the solutions, so there is not so many issues. Okay, so I want to do at least problem 1 and 4, and maybe problem 2. Okay, I won't do the James Stein problem, but it's super exciting. Okay, right. So we have the following situation. We have a joint distribution that is very nice. It's basically uniform here. Okay. So this is our X and that is our Y. And we have basically got this situation that the X and Y are uniform here in this shaded region. Okay, so now we want to be able to access certain properties of certain estimators. So this is the Bayesian setting, okay? And one and minus 1. Okay, the base d square x bls hat of y. So from the Bayesian theory, you know that the base least squared of y, base least squares estimator of y is basically the one that minimizes the squared error. So the cost function a hat is the square. Okay. So now in this case here, you are looking for the conditional expectation. Okay. So now in order to figure out the conditional expectation, it is easier to figure out the pointwise conditional expectation, this value here. Okay, so now we split into two different cases, right? One case is y positive and one case is y not positive. Now, when y is positive, okay, so I want to make this clear. Basically, we attempt to find this guy here, okay? Now, if y is positive, so we are somewhere here, all right? So we're somewhere here. If y is positive, then what is our f of x condition on y equals to y in terms of x? Well, if y is positive, then x, as you can see here, only belongs to the interval 0, 1. So we have this situation, 1, 0, 1, correct? So this is our density when y is positive. And it is clear that the conditional expectation in this case here is equal to 1 over 2, right? So now, on the other hand, when y is not more than 0, then we have the conditional density being something else, okay? But looking at this picture here, you see, okay, here, what is x? X can range from -1 to 1. So you have this situation, okay, -1 to 1. This is my f of x, and maybe I should put x here. Condition y equals to y, which is negative of x. Oh, by the way, this notation of mine, right, is the same as f of x given y, x given y. Same thing. Sorry, I changed it there. So this is equal to expectation x equals to y equals to y equals to 0. Okay. So in summary, the base least squares estimator with y is half and 0. Okay, by the way, the mean here should be clear that it's 0. We don't need to calculate this. So here y is greater than 0, here y is less than 0, less than equal to 0. Okay, this is my convention. Okay. So hopefully this is not so painful. All right. Any questions? Any questions from the Zoom people? Okay. So I think it should be relatively straightforward. Okay. So the error variance of your estimator. So basically what we are after is lambda BLS, the variance, which is nothing but the expected value of lambda of x given y. Okay. So that is this guy here is the variance of x condition on y equals to y. Okay. And this expectation is over y. And this is by iterated expectations. So variance of x condition y equals to y. What is this? Okay. Again, there are two regimes. Y is bigger than, and our convention is below here. Okay. So so we have this density when y is positive, and we have this density when y is negative. So what is the variance here? All right. For a uniform distribution, you can look up Wikipedia. The variance is b minus a squared over 12. Okay, where the b and the a are the endpoints. Okay, so here the endpoints are 0 and 1. So the variance here is 112. All right. So here the variance is bigger. So the length is 2. So you have 2 squared over 12, which is how much? 4 over 12, 1/3. Okay. So this is the how to get this. Basically, you apply b minus a squared over 12. Right. That is the variance of a uniform. That is a matter of calculation and bookkeeping that I will not do. Okay. So now what we have to do after we found the conditional variances is to find the base least squares estimator, which is the expectation value of this random variable, here. Okay. So basically we are averaging, right? So we have probability y bigger than 0 multiplied by the variance of x condition on y. Can I just be very lazy and just put 112 here? Okay, plus probability of y less than equal to 0 of 1/3. That's the meaning of average or expectation. Okay. Now, so what is the chance that y is bigger than 0? If you look at this, okay, so there are 3 equal squares here, right? So the chance that y is bigger than 0 is 1/3. Okay, it's uniform. So we have 1/3 times 112 plus 2/3 times 1/3. Okay, what is this? Everything turns out to be 1/4. Okay, so hopefully this is not too painful. Okay, the last part is the more interesting part. Okay, so now we were in the business of base least squares up to this point. So this is very standard. Okay, so now part C says we are going to modify the cost function to be the following. Okay, x minus x hat squared when x is less than 0, and x minus x hat k squared when x is bigger than 0. These sort of questions, right, originated. You must be wondering how come I have so many imaginative questions. All these were designed when I was a graduate student, together with my fellow TAs. So they were very creative. Very creative, these questions. Not so easy. Okay. I couldn't have come up with these questions in 1 week. These will come out. These I copied from a long time ago. So now let's try to figure out the MLS estimator. All right, modified least squares where k is some constant. All right, here they say k greater than 1, but later on let's try to examine the cases, right, where k goes to 0 and k goes to infinity, and let's see what these mean. That is the interesting aspect. These two regimes, okay, k go to 0 plus and k go to infinity, because there's nothing restricting us from taking these two limits, right? And let's see something very cool. Okay, right, but before we can see something very cool, we have to actually do the math, right? Okay, so now you notice we want to find this. Okay, so we're going to find this out. So if y, now I really need the picture. So you notice that if y is bigger than 0, then x is also bigger than 0. So this is the easy regime, right? So here in this case, if y is bigger than 0, then x is bigger than 0. Okay. So x of MLS. So in this case here, x of MLS hat y is equal to x of base least square y is equal to half. And the reason for this is actually not so trivial. Okay, is equal to x of base least squares y is equal to half. Now, when y is bigger than 0, you have this point here. You are here. Okay, here. And now x is bigger than 0. So we are in this regime here, right? So there is the additional k. There is additional k here. So it's not so simple. But this is just a scalar multiple of the original cost function. And we plug it into the Bayesian formulation. This makes no difference. Okay. So we get the same estimator here. Okay, this is really, really important. Okay. It's a very creative question. So you get this, you are in this regime here, you are in this scenario here because I say y is positive, so you are here, x is positive as well. So you're basically we are in the situation where the density is uniform here. 1, 1, 0. This is f of x given y equals to yx. You are in this scenario here as usual. Okay, and you are asking, okay, now I have the mean squared error scaled by something. Where is my average? Okay, where is the minimum cost? It's still half. Okay, it's still half here. Okay, so this is the scenario. Right. So the difficult regime, right, is the other side, is if y is negative here, right here. Okay, so let's write out the formulation properly. The modified loss is going to be we are trying to find argmin over A of C of x of A, f of x given y, x is given y, dx. Okay. Now, we have already figured out for y bigger than 0. So it remains to figure out the MLS modified least squares for y less than 0. Okay, we are going to call this function the objective function. Let's call it JA. So let's figure out what is JA. Okay, the limits here, when y is less than 0, I'm only concerned with y less than 0, okay? So y less than 0 means y between -1 and 0. So y here belongs to this. Okay, this limit goes from -1 to 1. The x can only go from -1 to 1. Okay, the x can only go from -1 to 1 because we are here. Okay, so now we have to use our brains to think very clearly. So we are going from -1 to 1, but then there's a difference in cost. There's a difference in cost when x is negative and x is positive. So we are going to cut off like this. All right. C of x a, f of x given y, x given y dx plus the same thing, but I am going to massage the limits here. Copy and paste here. Okay, I've got these two pieces now. Okay, 0 to 1. So this is a natural split. So now on the left hand side, we have the mean squared cost, or the Bayesian, or the what do you call it, this cost here. Okay, and this now here is uniform and takes on the value half dx. 0 minus 1 plus integral 0 to 1 x minus a with a k here squared half dx. Because this cost function here is k times x minus a squared. Okay, now over on this side here, x bigger than 0. Okay, I make an annotation here. For this side here, when x is bigger than 0, the cost is k times of x minus a quantity squared. On the other side, however, this side here, then the cost is the regular x minus a squared. Okay, so now we can do this. We can do this integration and so on and so forth. I'm not going to do it. So dj by dA is equal to 1 minus k over 2 plus a1 plus k. Okay, so this is a matter of integrating and differentiating and how to do it. So this one you set to be equal to 0. And so your base least or modified least squares, if you wish, solution is half of k minus 1 over k plus 1. Yeah, I think if you solve this equation, you get this. So at the end of the day, your modified least squares estimator takes on two forms. We know y greater than 0 is easy. If y greater than 0, okay, we have this scenario that x is bigger than 0. So here, in this case here, we have that the cost here is k x minus a quantity squared. Okay, so it's not changing with x. Okay, so when we minimize it, life is still simple, and this is nothing but half. Okay, when y is less than 0, then this is half of k minus 1 over k plus 1. Okay, let me see. Okay, half. Let me write it as half times k minus 1 over k plus 1. So that is the solution. It's a bit bizarre, right? Okay, so that's the solution for part C. Okay. Okay, so part D is the interesting part, and that's the interpretation part. And these questions are very good. They illustrate a point. I cannot design these questions unless I think for a long time. But any questions on this calculation? Any questions? This integration I will not do. If I do the integration here, I will make a mistake. Any questions? from the audience? Okay, so now what happens is let's interpret this result. Okay, so in the case y is less than 0, the cost function is a scaled version of the original BLS cost function. So estimator stays the same. On the other hand, if y is bigger than 0, of course, from the looks of it, the estimate looks rather different. But let's do a sanity check. K equals to 1. All right. If k is equal to 1, right, then XMLS for y positive is equal to 0, which is the same as this part here. So we didn't do anything bizarre in the case where k reduces to 1. Okay, so what does it mean for when k tends to plus infinity? Then XMLS y is equal to half, right? What does it mean for k tends to infinity? All right, so what it means here is that this part is very, very costly if you make mistakes. This part here is very, very costly. So now y is negative. We are living here. And our distribution of x is uniform from -1 to +1. Okay, so in this scenario here, let me just draw a picture. Our f of xy equals to y of x here is uniform from -1 to 1. Okay, and this is half. Now, if the k is equal to 1, we will decide here. But if k is going to infinity, and let me make an annotation here. The cost here is kx minus x hat squared. The cost here is x minus x hat squared. Okay. Now, if k tends to infinity, it is very costly to make errors here. So we will bias our decisions to this point here, okay, which is equal to half, because it is very costly to make errors on the positive real line. So we will bias our decisions to believing that x is actually on the positive half, and that biases, when you take the limit of this as k tends to infinity, you get half. See, there's a moral of the story here. Okay. And so what if k tends to 0 plus? What if k tends to 0 plus? Okay, if k tends to 0 plus, then what do we get? Okay, x MLSY is equal to minus half. Right? You put k equals to 0 here, minus half, right? So what does it mean? Now, if k tends to 0 plus, now this is inconsequential, and the cost incurred is over on this side here, mainly on this side. So we had better not make any error over on the left-hand side. Okay, left is over here for you. So here, what we will decide is that in this scenario, we will decide that x is equal to minus half. If k is super small, because if k is super small, the coefficient 1 here is much larger than k here. So these are the two extremes. Cool, right? I think my office mate designed this question maybe 10 years ago, more than that. Any questions? As I said, I want to do question 4. The rest you can read. Any questions on this? This is the method of differentiation. And what is the story at the end? Right? Okay. Now, finally, we can do question 4. All right, this illustrates the point. So we have the non-random parameter estimation problem. Okay, so here we have, let me write this out in full glory. Okay, y1 is this, y2 is x plus w2. Okay, but these w's are very funny, right? The variance of w1 is equal to 1, and the variance of w2 takes two values, 1, 2 when x is bigger than 0 and x is smaller than 0. So here x is not 0, so we only need to specify when it is positive and negative. This question is really beautiful. I don't know who created this, but it illustrates the point that we are trying to make in our discussion on non-random parameter estimation. So the question A asks you to compute the Cramer-Rao bound. So this one is a mechanical thing that you should know how to do, okay? So by the way, these are zero mean, the WIs, zero mean Gaussian random variables. Okay, so let's compute Fy, y parameterized by x. So here y is the vector y1, y2, and y is the vector y1, y2 realization. Okay, so when x is bigger than 0 and when x is smaller than 0, there are some differences. Okay, when x is completely bigger than 0, okay. Oh, by the way, the wi's are independent. Otherwise, you cannot do things. Okay, so now this is given by Gaussian when x is bigger than 0, y1 evaluated at x and variance 1. This comes from here. This one comes from here. Okay, and what is next is Gaussian y2 x. Now x is positive, right? 1. And this comes from here. Got it? Okay. So I'm going to move this down. Okay. So this is for x greater than 0. How about x less than 0? Okay, this part stays the same. But now this part here, the other part takes the form x2 squared. Variance, no, not 2 squared, just 2. This comes from here. Okay, and the green one stays the same. Okay, so that's the density. Okay, when x is greater than 0 or x is less than 0, we have these two densities. Okay, okay, so now it's a matter of differentiation. Okay, so you need to know the densities of these Gaussians, but it's a matter of differentiating. So I will not belabor the point so much. It's a matter of you looking up some table. Okay, so this one is up to some constant minus half y1 minus x squared minus half y2 minus x squared for x bigger than 0, and minus half y1 minus x squared. This is the exponent up to a constant here. All right, we are only interested in the exponent. 1 over 4 y2 minus x squared x less than 0. So the why is 1 over 4 is because the variance here is 2. You know, for Gaussians, the exponent is e to the minus y minus x squared over 2 sigma squared. So this sigma here gets translated into 2 times of 2. 2 times 2, 4. Okay. So for Cramer-Rao bound, we can differentiate 2 times. Okay. So d by dx squared log fy y parameterized by x. So we differentiate 2 times. Okay, these are all quadratics, right? Quadratics, you differentiate 2 times, you get constant. Right? These are all quadratics. So we are going to differentiate 2 times straight away, okay? So the coefficient of the quadratic here is half. The coefficient of the quadratic here is half. So you differentiate 2 times here, you will get the minus 2. Okay, you need to bring the 2 down. Then 1 plus 1, yeah. Okay. So if you differentiate this thing twice, the linear term gets cancelled. The constant term, of course, gets cancelled. And so you are only looking for the coefficient of the quadratic term. The coefficient of the quadratic term here is half. Now, if you differentiate twice, you will get 1, right? Minus 1 minus 1, we minus 2. Okay, the other one requires okay, if you do this slowly, you will get it right. If you do this so fast like me, you get it wrong, right? So this is x greater than 0, x less than 0. Okay, now differentiate this. From here, you will get a -1, and from here, you will get a half. Okay, so with careful bookkeeping, this is -3/2. Okay, so now we have that the Fisher information is given by the negative of the expectation. Okay, remember the definition. We are using the other form. This form is usually more convenient. So this has two forms. Okay, so one of them is 2 and one of them is 3/2. There is no need to take expectation over y anymore because these are constants, right? These are constants you plug inside here. This is an expectation over y, but these guys here are no longer functions of y anymore because they get differentiated out. Okay, so we will just negate an x bigger than 0, x less than 0. Okay, these are not random variables anymore, they're just constants. So you take expectation, you get what it is, but you need to keep this minus. Okay, so the Cramer-Rao lower bound reads that for any estimator, lambda x of x is bigger than, when x is bigger than 0, x is less than 0, it is 1/2 and 2/3. Okay, so that's a Cramer-Rao bound. Okay, show that a minimum variance. This is the exciting part. Does anyone have any questions on the non-exciting part? This is the non-exciting part where we just do bookkeeping. But we have to do all this bookkeeping to get to the exciting part. Any questions on the bookkeeping part? So the Cramer-Rao bound says that the variance is at least the reciprocal of the Fisher information. Okay, so you take the reciprocal here. Okay, right. Show that a minimum variance unbiased estimator does not exist. Okay. So we are given this estimator. I don't even know how the person who set this came out with this. So x1 hat is equal to y1 plus y2/2. Oh, I know how she came out with this. This another office mate of mine, the brilliant people. X2 hat is a 2y1/3 plus y2/3. Okay, so we have these two candidate estimators. All right. Now let us check that they are unbiased. Okay. So x1 hat, this is a function of y1, y2, right? So we can write x1 hat y1, y2 like this, but it's a bit long-winded. So let's just write x1 hat like this. Okay. So this is nothing but half of expectation value of y1 plus expectation value of y2. But y1, y2, okay, they are always centered at x, right? They are always centered at x. So the mean is always x. So this is a half of x plus x, which is equal to x. So we are x1 is unbiased. So by a similar logic, this is also unbiased. Okay, I think I don't need to calculate this because these two coefficients add up to 1 nicely. Okay, so these two people are unbiased. So now let us compute the variances. Variance of x1 hat. Okay, so variance of x1 hat is equal to how much? All right, so we have now y1 and y2 are first and foremost independent because the noises are independent. And this is 1/4. You need to square the constant, right? Variance of y1 plus 1/4 variance of y2, right? Okay, so this one is how much? Okay, now here we have to be super careful and we have to go back to our definition. So when x is greater than 0, the variance of y1 is 1 and the variance of y2 is 1. So let's put it down here. So when x is bigger than 0, we have 1/4 plus 1/4. right? 1 plus, well, the variances are 1, 1. So this is 1/2. Okay, when x is smaller than 0. All right, let's go back here. Unfortunately, we'll go up and down and scrolling a bit. So the variance is 1 and 2, right? The variance of y1 is 1, the variance of y2 is 2. Okay, so what we have here is 1/4 times 1 plus 1/4 times 2, right? So how much is this? 3/4, I think, right? Okay. So my math here, my mental calculation here is 3/4. Okay. So we have to be very careful here. So now variance of x2, our other alternative estimator, x2 hat. This is x2 here has these coefficients, 2/3 and 1/3. So 2/3 squared is how much? 4/9 variance of y1. Okay, here we have 1/3, right? 1/3 squared is how much? 1/9 variance y2. Okay, so now in the case x bigger than 0, this is 1 and 1. We have already said before. Now, if x is less than 0, these are other things. 1 and 1, right? 1 and 1, so this becomes 5/9. Because 4/9 plus 1/9 is 5/9, right? So when x is less than 0, however, we have to be careful. 4/9 times 1 plus 1/9 times 2, right? Because the variance of y2 when x is positive is 2. So how much is it? 6/9, right? 6/9 is 2/3. 2/3. Wow. So what do we have? Let's do a plot here. Okay, let's do a plot of the two estimators as a function of the variances of two estimators as a function of x. So for x1, the variance, as you can see here, is 1/2 3/4. Half is here, and 3/4 is here. Okay, so this represents the variance of x1 hat, and this is x here. All right, and this is 1/2. This is 3/4. Now this is going to be very ugly, this picture. And now when variance of x2 is 5/9 for x bigger than 0 and x less than 0, 2/3. Where's 5/9? 2/3 is slightly less than, okay, so this here. This purple line is 2/3. And then 5/9 is slightly more than half this here. Okay, so this is 5/9, and this is variance of x2 hat. Okay, so you can see this. So what would you see? Let me make this more straight. This 3/4. Okay. Actually, I can make straight lines, right? But you can see something. All right. You can see that one estimator is better than the other in either the positive half or the negative half space. But what does our Cramer-Rao bound say? Where is our Cramer-Rao bound? Here. Here, what the Cramer-Rao bound is saying is that no estimator can have variance smaller than half when x is positive, and no estimator can have variance smaller than 2/3 when x is negative. Cool. So now what happens here is that you have the Cramer-Rao bound saying what they say. The Cramer-Rao bound is this. Let me copy it so that I don't have to flip up and down. Okay, let's recall the Cramer-Rao bound where we derived. The Cramer-Rao bound is given by half here, the Cramer-Rao bound, and 2/3. So the two different estimators achieve the Cramer-Rao bound in different regimes. Okay, so it appears that, so what happens here is that x1 hat achieves the Cramer-Rao bound, Cramer-Rao bound, if x is positive, and x2 hat achieves the Cramer-Rao bound if x is negative. So any valid estimator does not know x. Any valid estimator should not know x, should not depend on x. But if we want to achieve the Cramer-Rao bound from these two estimators, we need to know x in order to see whether x is positive or negative, to use whichever one. So there's a problem. We cannot get a single estimator that does not depend on x. That doesn't depend on x. That touches the Cramer-Rao, that achieves the Cramer-Rao bound for all x. So these two estimators are not plucked out of the air. They are designed to be the estimators when x is positive and when x is negative. All right. They are basically the derivatives of this when you set them to 0. Okay. So this is an interesting question. It is reminiscent, or it is the question. It is how to say. It is a concrete example for this picture here. You know this picture? Okay. What picture? This.
Just to ask, right? Why should your potential NDU estimator be related to x1 and x2?
No,
X1 are just two possible estimators, right?
Yes.
Whereas your efficient estimator, your efficient estimator doesn't have to be related to x1 and x2.
Yeah, it doesn't have to be, but there are two estimators. Okay, yeah, that's right. These two estimators are estimators that are potential achievers of the Cramer-Rao bound, but they achieve the Cramer-Rao bound in two different regimes, x positive and x negative. So in order to use these two estimators, you have to know the sign of x in order to touch the Cramer-Rao bound throughout. To be more formal, indeed, we have to look at all possible estimators and not just x1, x2 like that, x1 hat, x2 hat like that. To be more formal, to do this question properly, we actually have to show that a minimum variance unbiased estimator does not exist. So we have to go through all possible unbiased estimators that are touching the Cramer-Rao bound in some regime, okay, and potentially have minimum variance. So this left-hand side, this x1, is the estimator that is the minimum variance on the right-hand side. And this x2 is the minimum variance unbiased estimator on the left-hand side when x is less than 0. There are no other alternatives, but this requires another argument, right? This requires yet another argument. This calculation here is probably not sufficient. It's not sufficient because we have not ruled out any other estimators, but it should be clear that there is no other one because these two are not plucked up from the thin air. Even though it's given in a hint, is by differentiating this, is by maximum likelihood for right-hand side and left-hand side. Yeah, it's not plucked out of the thin air, right? Okay. So this example actually illustrates this picture that I drew last time. You know this picture I drew? Yeah. That you don't have one uniform, one estimator that has smallest variance for all x.
Oh, so wait, so it's the argument that we try to choose maximum likelihood for left side, then we try to choose the right side.
Yeah.
But see, choosing maximum likelihood on either points shouldn't matter. Like when you find a maximum likelihood, you find it on a time-wise level, right? Yeah. But then you realize that these two only optimize on each side. Yes,
optimize on left side and the right side. So it should be clear that there isn't any other option. Right. So these two optimize the likelihoods on the left side and the right side. Okay, so this is the next. This is the question. Okay. Actually, question 2 is also quite interesting. So I'm not okay. This is quite interesting, but I'm not going to go through all the detailed calculation because you can just look at the algebra. But let's look at this question. Okay, 2. So we have this now we have a discrete case, which is geometric starting at 0. So y here is geometric starting at 0. Let's try to find the MLE, right? So the MLE requires us to differentiate with respect to the parameter. Now the parameter is called Q, it's not called X, but hopefully you're accepting this. YQ. So you're differentiating with respect to Q of log Q plus Y log 1 minus Q. I prefer to take logs. And so now after you differentiate this, you get 1 over Q minus Y over 1 over Q. You set this to be equal to 0. And after you are said and done, right, you will have 1 minus QY equals to 0. Is that so? Then you will have Q maximum likelihood as a function of Y to be 1 over 1 plus Y. Okay. Yeah, so that's the maximum, that's the quick way of getting maximum likelihood estimator for a geometric distribution starting at 0. Oh shucks, I pressed something. Oh, okay, good. Okay, so so the question is whether this is unbiased. So let's see. So we are going to show that it's not unbiased. So we have to plug this in this way. So we put in the capital Y. So we have expectation value of 1 over 1 plus Y, right? Right. So this is expectation value. The randomness is over Y. Okay. So what is the meaning of expectation? We are summing over Y equals to 0 to infinity of the 1 of over Y plus 1. That's from the 1 plus Y, and the density, or rather the PMF, is Q, 1 minus Q to the power Y. Is that so? Yeah. So when Y is equal to 0, everything becomes beautiful and you get Q. When Y is equal to 0, so that's Q. Then you have this extra stuff when Y starts from 1. Okay, and you have Q1 minus Q to the power Y over Y plus 1. So this is strictly bigger than Q. So we are not unbiased. Okay, so this is unfortunately biased. Okay, biased estimator. Okay, right. So nevertheless, okay, fine. Okay, so this is not going to be efficient, right? So B, your Bayesian friend. So who is a Bayesian here? I don't know. So someone is a Bayesian in the audience, and they suggested to treat the random variable X that is uniform on the interval 0, 1. So find the base least squares. So this is like a very nice problem that links base least squares to non-random parameter estimation. So someone believes that the unknown parameter for the geometric is uniform on 0, 1. And so now we can find the base least squares estimator. So this is nothing but the conditional expectation. Okay, so this is equal to integral of X of the posterior dx. Okay, so now after some calculation, X, you have to flip this around to Fy, y given X, f of X dx, and you move this upstairs here. Now you integrate this with respect to X, and then you have this other term that is in the bottom, Fyy, right? Then you have to integrate f of y given X prime fx of X prime dx prime. I'm skipping like 3 steps. But X here runs from 0 to 1, 0 to 1. Okay. Now you use that thing there, you use that the integral thing there, and you will notice that right, you have 0 to 1, X here, f of y given X is f of y given X is basically given by so let's put So this guy is equal to 1. This guy is equal to 1 throughout. All right. So f of y given x, you have x squared here, 1 minus x to the power y dx. All right. So this one of the x's here comes from here. Another one comes from the geometric. Okay. So this is too fast. Let me do this. The x comes from one of the x comes from here times x. And this guy is equal to 1, so this guy is equal to 1, so we ignore it. This guy is equal to 1 since uniform, since your friend is a Bayesian. Okay, and so x of 1 minus x to the power y, right? Dx, and the bottom is almost the same, except that you only have one copy of x, 1 minus y dx. This is x here. Okay, so you use the formula, and I don't want to belabor the point, you'll get y plus 3. Okay. Now, then you can ask the question, is this a bias estimator? Okay, but the next part actually is quite interesting. This algebra, I won't ask you whether you have questions or not. Figure out the algebra, right? So we have a certain estimator, and we can determine the relative bias. Okay, now there's a multiplicative bias here. Usually we talk about additive bias, but this is multiplicative. Okay, right? So this x over the estimates of x. All right. So we hope that this is 1. Then there is no relative bias. And surprisingly, the above two estimators are relatively unbiased. So this is equal to 1. Very cool, right? So we'll prove this for part 1 for the maximum likelihood estimator. So our maximum likelihood is equal to expected value of x over, now that was 1 over y plus 1. That was the maximum likelihood estimator, correct? All right. So this is equal to expected value of xy plus x, I believe. So wait. So this is x, y plus, right? So so that was fixed. Sorry, this is equal to q. That was the unknown parameter. Okay, because this is the maximum likelihood case. We are after we want to try to target x, which is equal to q, deterministic, non-random parameter estimation. So we have y plus 1 multiplied by q here. There's no distribution on x. X is deterministic, so I cannot put capital X there. I was wrong. Okay. So we can bring out this, and we have expected value of y plus 1. Okay. But in the case of geometric that starts at 0, the geometric that starts at 0 has this mean. Okay. Okay. So this I better put 1 plus y is better. Okay. 1 plus y for the geometric that starts at 0, 1 minus q over q. All right. So this is very beautiful, and this ends up to be 1. Right. After some algebra. Okay. So we will not do all this algebra. So R of the base least square estimator, right? This requires a bit more work because now x and y are both random. So we have x over the estimate. The estimate is this 2y plus 3, this one here. So what we have is 2 over y plus 3. And so this is equal to half of expected value of xy plus 3x, is it? 3 expected value of x. Okay. So this is going to be 1 as well after some calculation. But let us calculate the xy here. Okay. So this is equal to, okay, because the expected value of x is half. This is half. This part here is half. So this is almost trivial. So this guy here is a bit involved. All right. So let's just think about it. So this is by conditional expectation, xy conditional x. You can do this. All right. But now you can bring out this x, because if you condition on x, you know what is x, so it can come outside. So you're left with this. All right. So now what happens here is that now you have to figure out now you have to do a side calculation and figure out what is expected value of y, condition on x is equal to x. Right, you have to figure out this out. Okay, how to figure this out? So if x is equal to x, what is the mean of y? It is equal to 1 minus x over x. Because this is a geometric that starts at 0. A geometric that starts at 0 has this mean. Okay, so you have to put 1 minus x over x on top here. Okay. So now we have this is expected value of 1 minus x, which is equal to half. Because the expected value of x is half, the x here cancels nicely. So the relative bias of the base least square estimator, if you assume a uniform prior, is half into this guy here is equal to half. Half into half plus 3 over 2. 1. Amazing. Whoever said this question.
How do we understand this? Right? because the additive bias there is additive bias, but there isn't this sort of what do you call it? Relative bias.
Multiplicative bias or relative bias.
In that case, how should we understand this notion of bias?
Well, there are just two different metrics, right? Here, there are just two different metrics. You can think of the additive bias as one form of goodness of fit. Okay, if you want to use the Cramer-Rao bound, you have to have an additive bias of 0. But this is a multiplicative bias, a different thing. But multiplicative and additive, right? They are quite different and they play different roles in analysis, right? So if you have, it's not always true that if you have multiplicative bias, if you converge, or how to say, let me give you another, let me answer this, let me not answer your question, let me answer some tangential questions, okay? So if you have this sequence xn over yn converge to 1, right? So this is like multiplicative, this is like the relative convergence is like multiplicative. So this absolute value is 1, is close to 1 plus minus epsilon. But then sometimes we also want to converge in this way. So this one is like the additive type of convergence. So these two play very, very different roles. And one does not really imply the other or otherwise. So this could be the limit of y and go to infinity. All right. So these two are very important in different scenarios. But in this context here, right, you could have an additive bias of not 0, so you are not unbiased, but you could have a multiplicative bias that is 1, that you are multiplicatively unbiased. Okay, so these are just two different metrics.
Is there a way to explain, like, say, as a metric, what does the additive bias measure? As a metric, what does the relative bias measure? Because like one is additive, right? It's xn minus yn, whereas the other one is xn over yn.
Hard to say. Yeah. So yeah, I pointed out as xn over yn will converge to 1. Sometimes we want xn minus yn converge to 0. These are measuring different things. One is measuring. Actually, this one, you're measuring the different scales. So your yn could also converge to something very small, but you want your xn to track it in the multiplicative sense. Then here you want, it's a different thing altogether. I don't know how to answer this question. Yeah. So in any case here, we just want to calculate these two and show that there's some strange thing happening. In the Bayesian case and both in the Bayesian and non-Bayesian case, these are all one. Kind of strange. Okay, I think I didn't answer all questions satisfactorily because I didn't think hard enough on this. But I just wanted to show you how to calculate some things in this problem set. Yeah, we can all think a little bit harder about what this means. Okay. Right. So this brings us to the end of the semester, end of the course, and the end of the semester, which is very sad. We can have other sort of meetings. If you have any more questions about the past year exam questions, I'll be happy to answer. Maybe we can have the consultation hours at our regular time on Thursday. Okay, up to the exam. Okay, but you can try the previous year's exams. It's going to be the same format. But this last year, right? Last year, what happened was that suddenly there was a pandemic, right? So I made the exam simpler. So this year, by definition, the exam will be so simple because everyone is used to the pandemic. So last year, my exam, has this true/false questions. I don't have any more true/false questions now. So everything will be calculation and proof. Okay. So I don't really like true/false questions. But last year I was trying to do something different. But if you look at the previous years, I have no true/false questions. So there will be one question on probability. Okay, what? Let me write down. I still have tons of time, right? Okay. Perhaps it's the most important thing I'll say today. Exam format. Question 1 is on probability. What do we need to know? What do we need to know? What is my favorite? Exactly. Conditional expectation, which is related, as you know, to the base b squared. Okay. What did I set? Forgot already. I said some very esoteric questions. Maybe you need to know something about moment generating functions. Because I also like that. Let me see. It's all here. It's better for me to say the right thing. Convergence is very important also. Yeah, but sometimes I'm not in the mood to set such questions. Oh, yeah. What's my favorite thing? Conditional expectation. Moment generating function. You can also talk about convergence if you wish, okay? As you know, my favorite thing is conditional expectation in probability because it's really important. In real life, we use it. In real life, you split events into different things. Okay, so we will also have to talk about, we will have to revisit Poisson processes. Okay, so in particular, you have to know the properties, the usual properties of Poisson processes and do some basic calculations. You have to know what is stationary increment property and independent increment property. And you need to know how to do some algebra here. Right? And you need to know how to do some calculation, like if I have a certain interval here, what's the chance that I have 5 people arriving in this interval? Okay, so that's Poisson processes. And that's it. Q3 is of course Markov chains. Okay, I'm not very creative in Markov chains questions. So you need to know classification of states. Classification of states. You need to know about period of states. You need to know how to find the stationary distribution as usual. What else do I like? Convergence rate, yes. I love convergence rates. Lambda 2. And what do I like? So absorption probability. Absorption, expected time to absorption. Okay, and that's it. So how long do I need to wait to get absorbed into this absorbing state? Absorbing state means that once you are there, you get trapped there. Okay. Finally, we need to know how to do detection and estimation, hypothesis testing and estimation. So in the detection part, you need to know how to do. You need to know how to set up a hypothesis test. You need to know how to set up a hypothesis test. You need to know whether or not something is a sufficient statistic. And you need to know how to compute probabilities of error, both type 1 and type 2. What I call type 1 and type 2? False alarm and misdetection, basically Q0, Q1. Okay. Estimation, as we have just discussed, we need to know how to compute bias, whether something is unbiased or not. We need to know how to compute the Cramer-Rao bound. We need to figure out whether something is efficient. or not. We need to know things like ML estimation. We need to know how to compute the maximum likelihood estimator. And we need to know how to compute its variance and compare that to the Cramer-Rao. So see, we didn't learn too many things. We only learned this. Okay? Yeah. So, oh, sorry, this green part is probably not so clear to the people here, but it's clear to the Zoom people. Yeah, so you need to know all these things, right?
Wait, just to check, Pearson Neyman.
Oh, Neyman-Pearson. It's not Pearson-Neyman.
Sorry.
Pearson-Neyman, you confuse me. Neyman-Pearson is captured in here. Right. You need to know how to. I love to do Neyman-Pearson from previous years, as you know. Suppose your boss asks you to design a test that has false alarm probability 1/100. Then what is the best misdetection or detection probability? Randomization. Yeah, so forgot to say. When should we randomize or not randomize? Okay, so I love to do this randomized thing. If you notice yeah, so this is what we learned. I will not, let me take that back. I will set some a bit challenging questions, but most of the 90% of the questions are covered like here. Okay, quite standard. Some require some higher order thinking, but really we need that. Okay, so I want to thank you very, very much for your kind attention. This is not the umpteenth time I'm teaching this class, but it's still very enriching, and it's so sad that I won't get to teach for 4 months. Okay, but it was a very great pleasure teaching. I'm so glad that even though we have the Zoom option, many people still show up in person, and many people still show up for office hours, and keep being enthusiastic. So thank you very much, and hope our paths meet again. Thank you. Yeah. Thank you. Thanks to the people in the Zoom also. All right. We will keep in touch, and we will have office hours as and when needed. Okay. Bye-bye. Bye.